In this video, we'll talk about the idea of increments and of differentials, and we'll look at how they're related to one another and basically formulas for each one, and then we'll do some examples of those. So let's start off. With a with the basic idea. All right, we have an increments, and increments will usually be represented by delta. So delta x would be an increment in x, delta y or delta f would be an increment in the function value or the y value. Usually they're the same. All right, then the differentials we represent with a d. dx is the differential in x, and dy or df is the differential in y or f, and again these are the same thing. Now usually for the independent variable, the input, the increment and the differential we'll consider to be the same thing. Let's take a look at this graphic and see what everything is. So suppose we start with x0, and so we have here on this graph a point x0 and then f evaluated at x0. All right, that's a point. Now let's suppose that x undergoes a change. And if x undergoes a change, all right, the y value on the curve will undergo a change. All right, will be at this point, will be at x0 plus delta x, and the function value will be f of x0 plus delta x. And so we'd have here, if we would look at this, how much did the function value change by? Well, the function value changed by this much. This is what we would call the increment delta y or delta f. And notice that's what we have marked here. There's delta y. All right, again, if you start at the point x0, f of x0, and you ride along the curve to the point where the x-coordinate is x0 plus delta x. All right, the change in y, the vertical change for you along that ride along the curve, all right, is delta y or delta f, is the increment. All right, if f is differentiable at x0, we can calculate a tangent line. And if instead, if we started at the same point x0, f of x0, if we start at the same point x0, f of x0, and instead of riding along the curve, we rode along the tangent line to the place where x is, the x-coordinate is x0 plus delta x, or x0 plus dx. Remember, delta x and dx are the same. Then the change in y along that tangent line is what we call dy or df, which is the differential. These are known as differentials. All right, and these are the increments. Okay. All right, now let's see. Let's take a look and let's come up with a formula for the differential. All right, notice that dy divided by dx is the rise over run for this tangent line. So this would be the slope of the tangent. I'll call it m sub tan. But the slope of that tangent line is also given by the derivative at this point. So, all right, what we can write then is that this dy or df, clearing the denominator, is going to be equal to the derivative value times dx times this change in x. So the differential is given by the derivative times the change in x. Now, lots of times, well, let's take a look at something here. If we if we look at this, all right, in this diagram, we can change the values of x0 and of delta x and dx. Notice what happens, all right, we have this little error between delta y and dy, but if delta x is made smaller and smaller, notice that error, oops, I let it go here, notice that that error it shrinks away. That, sorry, I keep on marking that here, but if we do this, can you see that if I make delta y, or delta x, excuse me, or dx very, very small, then delta y and dy are almost the same thing. So the thing that we want to keep in mind is that for small delta x, which is the same thing as dx, delta y is approximately dy, or saying this in terms of f, delta f, remember delta f is the same as delta y, is approximately df. Okay, so let's take a look at a couple of examples where we're calculating increments. Remember, the deltas represent the increments, and where we're calculating differentials. So here's the function: f of x is equal to x to the fourth, or excuse me, 3x to the fourth, and x0 is equal to 2 delta x is 0.1. And what we'd like to do is we'd like to calculate delta y or delta f. Well, to calculate that, all right, we'll have to take the change in y will be the function value at the end after x has been changed minus the function value at the beginning. All right, this would be, all right, f of, well, x0 plus delta x is going to be 2 plus 0.1, f of 2.1 minus f of 2, and let's see, that would be f of 2.1 is going to be 3 times 2.1 to the fourth minus 3 times 2 to the fourth, and 2 to the fourth is 16 times 3 is 48, so this is going to be 3 times 2.1 to the fourth minus 48. And if I go back, that difference is about, you can check this on your calculator, 10.3443. Okay, so that would be the increment. That would be the increment. The f value at the end after the delta x has been added, all right, minus the f value at the beginning without the delta x. And of course, what's happened, it's hard to see on here, but at this point here, we've just changed, all right, we started at 2 and went to 2.1, which is a very, very small change, and calculated the difference. All right, and here I have that result here. I have that result. All right, okay, now let's calculate dy or df. All right, well, dy is going to be the derivative evaluated at x0 times delta x. So that would be, let's see, our derivative is going to be 12 x to the third, I'll say the x0 to the third, times delta x, and x0 is 2, so that would be 12 times 2 to the third times delta x, which is 0.1. Well, 2 to the third is 8, so this would be 12 times 8 times, I'm going to be careful, it looks a little like a minus sign there, all right, times 0.1. Well, 12 times 8 is 96, so this is going to be 96 times 0.1, or 9.6. And 9.6 is approximately, depending on how approximate you want to get, 10 0.3443. If delta x would have been a little smaller, like say 0.01, then these would have been much closer together. Right? But again, the differential can be used to approximate the increment. All right, and here we have it. Okay, let's take a look at another example. Let's suppose that we have f of x is equal to sine x. Oops, I think I missed an f here. F of x is equal to sine x. X0 is pi over 3, and delta x is negative 0.1. So let's calculate delta f. Well, delta f is going to be f of x0 plus delta x minus f of x0, and that will be f of excuse me, pi over 3 minus 0.1 minus f of pi over 3. So that will be the sine of pi over 3 minus 0.1, which you could get on your calculator, minus the sine of pi over 3. And let's see, let's recall, if I draw a right triangle here, this is pi over 3, or 60 degrees, pi over 3, not pi over 6. All right, then this side is 1, hypotenuse is 2, the opposite side is square root of 3. So the sine of this is going to be square root of 3 over 2. So this would be the sine of pi over 3 minus 0.1, all right, minus square root of 3 over 2. And if you calculate that out, we get about a minus 0. Maybe I should really put approximately, because this is not really the case here, minus 0.054243. Okay, and that would be the increment. All right, now let's calculate the differential. Okay, and the differential, remember, to calculate the differential, we take the derivative evaluated at x0, all right, times delta x. Okay, so in this case, the derivative is going to be the cosine, the derivative of sine is cosine, of x0 times delta x. And let's see, that would be the cosine of pi over 3 times a negative 0.1. And let's remember here, I always make sort of a wavy hypotenuse here. So let's see, this is pi over 3. So 1, 2, square root of 3. Cosine is adjacent over hypotenuse, so that's going to be 1/2 times a negative 0.1, and that would be 1/2 is 0.5, so this would be negative 0.05. And notice that that negative 0.05 is approximately the negative 0.05443. Okay, and so we have, again, as we said, that the increment is approximately equal to the differential, and I have this calculated out for you here, except that this should be, I think I have a typo here, minus 0.05. Okay, so we'll fix that. All right. Okay, and this is what the idea of a differential and how it compares to an increment.